Okay, so I think we can start. It's a pleasure to start the morning session with Marius Petropoulos that will talk about Carrollian momenta from anti de Sitter. So do not hesitate to ask questions during the talk. The only thing, please wait for the microphone so that it's easier. Okay, please, Marius.
Thank you, Andrea. Thank you for being here so early. I sympathize. This is about Carrollian momenta from anti de Sitter. So this is, somehow maybe a new part of this conference. This has not yet been discussed, and I'm glad to do it. Actually, this is a work, I will mostly be discussing a work that involves this list of gentlemen. I'm included in this list, of course. And, but it also refers to works that have been done with other people, and I have tried here to be exhaustive about the people and the institutions they belong to. All right, so let me start with setting up what I want to say. This is about, of course, the quest for a holographic correspondence, and this has been one of the main themes, actually, that were discussed since this renaissance of the asymptotically flat space-time interest that followed maybe the discovery of gravitational waves. And most of this quest has been focused on the scattering sector, and this has been discussed through the celestial approach, as well as later on from the Carrollian avatar perspective. Now, very few things have been done in relation with the original holographic proposal regarding a DSCFT. Now, of course, there is a good reason for that, is that going from anti de Sitter to flat is very hard. Usually it's singular. And it is clear that you cannot learn much unless you do things carefully. So let me maybe say a few words about comparing this anti de Sitter on the one hand and flat on the other hand. So the basic things in anti de Sitter, and I will here be referring to 4 dimensions exclusively, is that the asymptotic symmetry is the conformal group in 3 dimensions. Now, we assume saying so that you have taken the appropriate fall-offs and boundary conditions. Otherwise, you may have different groups, even bigger. And the solution space corresponding to this choice is made of 2 pieces, which is the metric, G mu nu, and what we call the energy momentum tensor, both defined on the conformal boundary. And Einstein's equations emerge as the requirement that this energy momentum tensor be conserved with a connection, which is the Levi-Civita connection on the boundary. Now, regarding a DSCFT, the very fundamental things, of course, this is very few things compared to what a DSCFT actually conveys, but the basic things is that there is a boundary dynamics, there is a background field G mu nu, and there is a conjugate momentum, which is the energy momentum tensor. The first plays the role of a source, the other plays the role of vacuum expectation value related to the first to the variation of the metric. And the conservation of the energy momentum tensor appears as a consequence of diffeomorphism invariance of the action or the effective action, which is on the boundary. Now, if you now compare to what's going on in flat asymptotically, in flat asymptotics for asymptotically flat spacetimes, first of all, the asymptotic symmetry group is infinite dimensional. This is BMS4, which is also the Carrollian conformal group in 3 dimensions. And the solution space has an infinite number of components, as opposed to G mu nu and T mu nu, which appear in anti de Sitter. Now, a common expectation is to define an energy momentum tensor and possibly interpret this energy momentum tensor holographically, referring to it as a VEV as opposed to the source. Now, I should say that this is to some extent wishful because it is maybe too much anti de Sitter inspired. I'm not saying that it is not worth, I'm just saying that the statement is not so clear. I would say that a simpler statement, even though you may find that it is tautological, is the following. Is there, so the statement is a question, is there a boundary dynamics with fields and conjugate momenta? This is the question that should be asked. Whatever you do, if you think that there is a sort of holographic relationship. Now, there are two ways, of course, to handle this question. First of all, directly from flat space-time, or as I will show, using the limit of anti-de Sitter. As I will show modestly, because many things are still under question mark, and here is a summary somehow of what I will be discussing. And the main message, by performing Laurent expansion of the anti-de Sitter boundary energy momentum tensor, which is a piece of information that we know, Laurent expansion with respect to the cosmological constant, we obtain what we are tempted to call as flat momenta, as well as their Carrollian dynamics. I will show how this goes. Of course, this is part of our understanding. I have to stress here that the boundary dynamics is not yet fully unraveled and many things remain to be done. So let me start, therefore. Yes, yes, please. Andrea, the microphone. Thank you.
So you mentioned two paths,
Yes.
the intrinsic and the limit from ADS. But
Yes.
I mean, there should be a third one, right? You could also take a limit from de Sitter. Do you have any comments on that?
Okay, so no, I have no comment. Actually, you are right. As a matter of fact, most of what I will present here could be extended to de Sitter. The only difference is that we have a poor understanding of de Sitter holograph. So in a sense, this could maybe shed some light on methods that we could use to extend our understanding to de Sitter, but I'm not claiming that I have that understanding. Okay. Thank you. Other question? All right. So let me therefore go to anti-de Sitter. I will discuss anti-de Sitter, and then next I will go to the limit. As a matter of notation here, this is what we call the bulk metric. This is the four-dimensional metric, capital G mu nu. And lambda, which is the cosmological constant, is related to k squared through this relation. This is in 4 dimensions. And of course, it is negative because I'm considering anti-de Sitter precisely. Now, we'll consider here the Newman-Unti gauge. This is, so the coordinates are, as usual, the radial coordinate r, u is the retarded time, and xi, I going from 1 to 2 are the angles on the celestial sphere. These are the gauge conditions that define the Newman-Unti gauge. We have been using the Newman-Unti gauge for our purposes. It's more convenient than Bondi. So the expression that you finally obtain, this is once you impose these conditions, is this expression. This is generically written. The functions which appear here are a priori arbitrary functions of all coordinates, so the radial coordinates, the time, and the two angles. And one of the features of this Newman-Unti gauge is that partial r is a null geodesic congruence are finely parameterized. This is the difference with respect to Bondi, where the r is not an affine parameter. Now, a feature which for our purposes is bad is that this gauge is not stable under transformation that I have noticed here, u general transformations of the boundary of the time of the boundary, u a function of u and x, and it's not stable either under rescaling, so Weil transformation I should say, so when r is rescaled by an arbitrary function of time and the angle. So this is the reason why we have moved to what we have called the covariant Newman-Unti gauge, and this has been referred yesterday in the talk by Mark, where he also was using this gauge to some extent. So the idea in this covariant Newman-Unti gauge is to trade the form du, so that u is the retarded time, into a more general form defined on the boundary. This defines the congruence on the boundary, and this depends on two functions which are omega and b functions of time and angles. This is a congruence which has been normalized to minus k squared. And remember that k plays the role of a sort of effective velocity of light on the boundary, and when the limit k goes to 0, this makes the effective velocity of the boundary vanishing, and this is how the connection with Carrollian geometry appears. Now, this is an incomplete gauge fixing. So it has consequences which I will not be analyzing here, but which have been discussed in the literature in the past. Now, once this is given, so this is given, this expression is given, we can expand the various functions which appear in this expression in powers of R. So I say here no logs for anti-de Sitter. This is not so important, but of course, for the asymptotically flat case, it's a specific requirement that could be actually waived. And this is the expression that you obtain. This is not yet solved. I mean, it's not yet a solution of Einstein's equations. So what appears here is just an expansion in powers of R at every order. And what you can recognize in this expansion is, well, let me start by the first term, the highest in power. So this is the term in R square with the ds square. This is what is interpreted later on as a boundary metric. And this boundary metric is expressed using a boundary Cartan frame. All right, this is a boundary Cartan frame. So the thetas which are here, the capital A goes from 0, 1, 2, and the little a, 1 and 2. Right? There are time direction and two space directions. Actually, this congruence that we have introduced to make the gates covariant in the sense that I have explained in the beginning is aligned with the zero component of the frame. So this is the velocity. Somehow this, I call it velocity, but it's a congruence. So this is given by this expression. And the A, which appears here, is just a Weyl connection. This is what makes it possible to have this invariance with respect to rescalings when R goes to B times R. The other functions which appear are arbitrary at this moment before solving Einstein's equations. And well, the decomposition that you see in this parenthesis is just a decomposition in terms of longitudinal components with respect to U, so theta 0, and transverse or mixed components, including also the theta A. Of course, all these functions have a specific Weyl weight because everything here is Weyl covariant, and the weight is just determined in terms of the weights of the other parameters or the other functions which appear there. Right, so are there any questions regarding this? So this is the starting point, right? Then we have to introduce this inside Einstein's equations, solve these Einstein's equations order by order in 1 over R. This is not something new, of course, this has been done in many gauges. I'm just here mostly setting what the notations are in order for the limit to be taken at a subsequent step. Okay, if no questions, I can therefore proceed. So inserting this in Einstein's equations order by order. So at highest order, which is R square, as I said, the coefficients is the boundary metric, and nothing constrains this boundary metric. So it's a three-dimensional metric, pseudo-Riemannian. It has 6 arbitrary functions which appear there, and these are free, and no constraints appear on these functions. Free, and of course, they depend on time, U, and angles, X. Now, at order R, what we find is that the coefficient CAB that actually is the shear of partial R, Einstein's equations demand that this shear be also related to sigma AB, which is the shear of the congruence U. So to make it clear, so partial R is a bulk congruence. And this has this shear CAB. U is a boundary congruence, and it has a shear sigma AB. And Einstein's equations require this to be equal with, of course, a factor k square between the two. So this solves order R. Then we go to the next, which is order 1 over R. Remember, if you take a look on the previous expression here, this is order R, this is order 1, not 1 over R, this is order 1. There is this function which is there, and then solving Einstein's equations makes this FAB just related to the boundary conformal Schouten tensor. Okay, till there is nothing really new. and nothing very exciting. Now, the only free functions we have are those of the boundary metric. So at order 1/r appear new things. So there you have this expression. Well, this expression is exactly the previous one. Simply, it is written explicitly. It's 1/r. There is a longitudinal part, the mixed part, and the transverse part. And there are arbitrary functions, which are epsilon, qa, which appears here, and tau ab. And these are 5 arbitrary functions. Arbitrary means that there are new functions. It doesn't mean that they will not solve an equation. This will come in a minute, precisely. Now, what is interesting to see here is that you can repackage these functions and build a boundary, what we call the boundary energy momentum tensor. So epsilon appears as the density, the energy density, q, the q which is hidden in the delta q, and I will say explicitly the difference between q and delta q in a minute. The q is the heat current, and tau ab is the stress. Now, the first remark that I have to say here is that in this gauge, the energy momentum tensor does not appear in a single block as it appears, for example, in the Pfeffer-Mann-Graham expansor. It appears at 1/r split in several pieces. The other remark that I have to say here is that the heat current and the stress, so the qa and the tau ab, appear in combination with 2 other tensors which are absolutely determined by the geometry, so by the metric. These are pieces of the boundary cotton tensor, which appear explicitly. So these are not arbitrary new functions. These are the pieces of the cotton tensor of the boundary metric. Now, this cotton tensor, therefore, to make it clear, the cotton tensor is also a 2-index tensor in 3 dimensions because the boundary is 3-dimensional. It's symmetric and traceless. And it can be decomposed again as a longitudinal, transverse, and mixed components. And what appear here is these are transverse components. This comes from the mixed, and this comes from the 2-index part, right? So the star is what we call a transverse duality. Star is just a transverse duality because you can define such a duality by considering eta ab, c, because this is available in 3 dimensions, and then you contract with u here c, and you have a 2-index tensor. This maps any transverse tensor into a transverse tensor. It should be symmetric and traceless, or a vector to a vector. So this is a technical side. It's not so important. I mean, it is important, but not to be discussed so extensively. So what appears in this, for this structure, now you have to demand that this obeys Einstein's equations at this order. And what you find is that Einstein's equations tell that the boundary energy momentum tensor should be conserved. Of course, the cotton itself is conserved, but this is not demanded by Einstein's equations. This is just an identity due to the structure of the cotton, right? And nabla is a boundary Levi-Civita connection. So at this level, at this stage, at 1/r order, we have introduced an energy momentum tensor as a new object, and this is demanded to be conserved as a consequence of bulk Einstein's equations. Now, if you go further, at any further order, you can repeat the pattern, but you won't have any new piece appearing. New functions will appear, but Einstein's equations will make them related to the ones that you have already introduced. So the metric and the energy momentum tensor in terms of algebraic and derivative pieces, right? So this is standard. Simply, I have here recalled how it works in the gauge that we have been considering. So let me make some remarks, also to try to connect with other talks. The first remark is that the boundary metric is x and u dependent. So this is a function of time and space. And in particular, the dependence of time makes it, this I'm referring here to Céline's talk, this depends on time, and this contributes whenever we are talking about gravitational radiation, this contributes, of course, to the gravitational radiation. If you clock it to be either constant or time independent, it does no longer contribute, other pieces contribute, right? So this is something that was quoted yesterday, and I wanted to say it here to stress it. And of course, this metric is not necessarily conformally flat. So we are somehow outside of the natural realm of the standard anti-de Sitter CFT. This is not necessarily conformally flat because the cotton which appears is not necessarily zero. So maybe to make also contact with other things that were discussed, for example, by Glenn and by Mark, this is a general expression. You can now tune it. You can demand that some of the pieces that were introduced vanish. And if you do so, you find what we call the twisting algebraically special spacetimes. Then it is resummed. These have a more compact form, as I have presented here. These are the ones that you can find. It was also quoted in chapter 29 of McCallum and other books. But here is including anti-de Sitter. So there is a cosmological constant. These are not necessarily vacuum solutions. I'm quoting them because I will be referring to them in a minute. All right, I think this is all I had to say about anti-de Sitter, about this construction. Like, and we summarize, there are two pieces of information, the metric and the boundary energy momentum tensor, and this is required to be conserved. Questions? All right, so let's now move to the case of asymptotically flat spacetimes, right? So with this set of informations, I want to again discuss this asymptotically flat spacetime as they appear from their null boundary and try to unravel what we would call momenta and the fields that are associated with those. So let me first give the spirit. So again, we want to recover flat solution space, the flat solution space, so the space of all the functions which appear, and this is accompanied, of course, with the equations that come together as a limit of the anti-de Sitter solution space. And of course, this is, this might at this stage appear difficult because anti-de Sitter space has a finite number of functions, and we here want to recover an infinite number of functions. And then address the concept and the origin of the boundary momenta and translate as much as we can the Einstein bulk dynamics into what we should say be a Carrollian boundary dynamics. Now, the idea behind that is to expand the arbitrary functions which appear in the ADS momenta, so the energy momentum tensor, the energy density, the heat current, and the stress, expand these functions in powers in Laurent series of k square. K square is related to the cosmological constant, and this is what ultimately we want to take going to zero. So therefore, I write here in a rather agnostic fashion without making any assumption the full Laurent expansion for these quantities. Well, I have here I have epsilon n. For the others, I have used different letters. Well, this is because some of those will vanish, some of those will be determined, and the others will be, again, free, right? So this is the pattern. It goes from minus infinity to plus infinity. And maybe I should motivate this choice, right? This is, as you can imagine, the various functions which appear in this expansion will be the pieces of this infinite dimensional solution space. But maybe I should motivate the reason why we have this expansion as starting point. And for this, I'm referring to these algebraically special solutions of Einstein's equations in the presence of cosmological constant that I mentioned previously, right? So you can take these solutions, consider their energy momentum tensor, and indeed observe that this tensor appears with several powers of k squared. Now, in order to avoid having heavy formulas, I have presented here the subset, which is called the non-twisting subset of this algebraically special solution. And this is precisely what yesterday Glenn explained as the Robinson-Troutman. Here is the Robinson-Troutman in anti-de Sitter, right? So this is the non-twisting subset of the algebraically special solutions that I presented previously. Remember, these solutions are solutions where you tune specifically some of the parameters. You tune them, basically you demand that the shear vanishes completely, and you demand that the energy momentum tensor, the heat current, and the stress be entirely determined by the cotton. No new functions appear. So the only new function here is epsilon, basically, for those. And so where, or M written here equivalently. Oh. Questo? Oh, sorry. So this is the metric of the Robinson-Trautmann, which appears. So in the parentheses that you find here, this is the ds square, the two-dimensional, the three-dimensional boundary metric. U is the time. Zeta, zeta bar are a parameterization of spatial section of this two-dimensional space, and P is an arbitrary function of U, zeta, and zeta bar. So all the quantities which appear in this expression are explained here. Everything is explained basically in terms of this function. Kappa is the Gauss curvature of these sections. Well, that's all I have to say. This is the expression of the metric, the bulk metric. Now, the momenta and the conservation of this energy momentum tensor are the following. Epsilon is related to M. These are functions, a priori functions of all coordinates, but okay, we have to introduce this in this equation to find what they look like. So epsilon, Q is determined in terms of the Gauss curvature. Actually, this is precisely a piece of the Cotton tensor because these are algebraically special. There is no new functions. The Cotton makes everything. And this expression is of order 1, whereas if you go to the stress, you find that it is of order 1 over k squared. And if you consider more general algebraically special solutions, you have several terms which appear at different powers of k squared. This is all to motivate why we have been considering this expansion, right? Now, if you demand this equation be satisfied, well, you find exactly the famous Robinson-Trautmann equation that Glenn has produced yesterday with a slight difference that I have here kept M general. So M could be here depending on time, but you can also gauge fix it and make it a constant. This was the equation that Glenn was presenting yesterday, right? So this motivates. I will not discuss Robinson-Trautmann here. It was discussed, I think, also during one of the talks by Marika Taylor a few weeks ago. This is not the purpose. This is to motivate why we consider this expansion in powers of k squared. Now, let me therefore move. Okay, it's also good to remind that this is what, when lambda goes to 0 in the flat case, this is the standard Robinson-Trautmann-Penrose diagram. And this is interesting because it's clear, this is a clear example where we are not considering in this framework just scattering between scri minus and scri plus. The situation here is more complicated because the system actually radiates and relaxes to a Schwarzschild solution. Again, this is a whole chapter that I will not touch here. Let me move now and explain what are the basic geometric tools before taking the limit. So the basic geometric tools, first of all, remember that theta 0 was the boundary one form associated with time, and this had this general expression. And there is a factor k here, which means that when k goes to 0, so when we consider the flat limit, this vanishes. And therefore, the limit of the boundary metric is singular in the sense that it loses one direction. Only two, the theta a's, the little a goes from 1 to 2. These are the two space directions. And therefore, this is only space direction, although the boundary is still three-dimensional. And this is what the Carrollian degenerate metric, which has one null direction. The kernel of this metric, which is the field of observers in the language of Carrollian geometry, is actually the time direction u, appropriately rescaled. And there is a dual form, which is what we call the Ehresmann connection, which is the theta 0 divided by k. So these are somehow the pieces of information that you have on the boundary. Here they are entirely captured in the forms and in the vector. So you have epsilon, which is the field of observers that defines the null direction on the boundary. Mu, which is the Ehresmann connection, which is the dual form. And theta 1 and 2 are the two spatial forms. All this depends, of course, on u and x, on time and angles. So these are the basic fields, I should say. Now, coming back to the original question I was quoting in the beginning, this should be considered as the background, well, the geometric background fields of the boundary. And the question, of course, is how their associated momenta look like, what equations do they solve, and what are the potential constraints that should obey.
The dynamics that you are going to get for this Carroll, it is the electric or magnetic version of it.
You're referring to which, the dynamics, you mean?
Sorry. I am referring, for example, that there is the electric Carroll gravity by Mark.
Yes, and magnetic, okay.
70s.
Yeah.
And also was some proposal.
No, I understand.
Magnetic Carroll gravity, and simply I would like to understand in doing that limit, in which place are we going to go?
I don't know if I should, I don't know how to qualify, because we are not finding a gravity. I mean, to make it clear, this is a good question, and maybe I should clarify this point. We are not considering the limit of the Carrollian limit of gravity, right? This is the zero cosmological limit of gravity, which is mapped onto a Carrollian limit of a boundary dynamics. But the boundary dynamics is not a gravitational dynamics.
But has been also studied the non-gravitational dynamics of a particle or a field and has the electric and magnetic description.
Yes, this is an effective description in terms of, a conservation equation. Now, I don't know whether I should call it magnetic or electric. But the question is good, because actually, if we want to move away from the effective dynamics to a genuine microscopic dynamics, then your question will make sense. Because in that case, you'll have, we will have either a magnetic or an electric. This is something that has appeared in the discussions of, the celestial related to Carrollian, and the question of being electric or magnetic is absolutely relevant. At this stage is effective. What we describe is an effective conservation regarding the momenta. And for this, I would have hard time to decide whether this should be called magnetic or electric. But maybe.
So, of course, this is, I guess, a bit conjectural, but I think it's neither, or rather both, because the dual field theory should have both magnetic features, namely related to black holes in the bulk, and electric features related to scattering.
Okay, this I sympathize with this. There are several sectors. As I said, this is a part of things that we do not fully understand. We expect several sectors to appear. And the sector of scattering and the sector of the bound states or whatever are different, and they will probably lie in different sectors of the Carrollian physics.
Yes, just to clarify a question, you said that you had these boundary background fields, but then you wanted to look for momenta for them, which makes it sound like they're dynamical because you're looking for momenta. So just to, when you say, are they boundary dynamical fields, or by background do you mean that they are non-dynamical?
Okay, so it's exactly, is exactly what I have quoted for the case of anti-de Sitter, right? For ADS, I said that we had G mu nu, which is a background field, and this is not dynamical. But you have an effective action, and it's a background field of this effective action. And from this background field, by varying this effective action with respect to this field, you define the conjugate momentum. This is the picture that we have in mind at this stage. This is the step number 0 of holography, if you like. You imagine that you have a boundary dynamics. The G mu nu is a background field, but it allows to define an energy momentum tensor or a conjugate momentum in general. And in the same spirit here, I have those fields which are there, and they will have conjugate momenta exactly in the same spirit. Simply that I have traded the pseudo-Riemannian boundary geometry of anti-de Sitter for a Carrollian Carrollian structure on the boundary for the asymptotically flat case. This is, I think, the best I can say. In a minute, I will add more fields, more background fields, and I will not discuss them so much, but of course, in this case, we will have more. But those are the fundamental ones. This is what we call the elementary Carrollian structure. Right? Okay, so let me therefore now proceed. So this is, as I said, these are the basic geometric tools. These are the things that appear, the first things that appear when you consider the limit k goes to 0. Now, what's next? Now, this is, well, in 2 words, how we can now, the way that we will proceed in order to unravel these dynamics and to unravel the various fields and momenta which appear. Well, we have to take carefully the limit k goes to 0 in the equations that we have. Basically, the equations that we have, remember, are the energy momentum tensor, divergence of the energy momentum tensor equals to 0, and another equation that were relating the shear, the 2 shears here. Remember, there was these 2 were equal. This is what I call on-shellness conditions. These are the conditions that appear naturally when you solve Einstein's equations in the bulk in the anti-de Sitter case. So we have to take these equations and carefully consider their limit when k goes to 0. The second requirement is that the line element, so the bulk line element, the solution, should remain finite. So in this solution, you have several inverse powers of k. So if k goes to 0, these explode, these create divergences, and you have to demand that the coefficient of these divergences be 0 in order for the final line element be finite. Right? So this is somehow the recipe that we have been following. And let me therefore apply this recipe order by order in the various terms as we did in the case of anti-de Sitter. So order R. Order R, remember this is R, the order R is where the C, the shear, appears, right? And here I quote that indeed, these Einstein's equations, remember, had required that k squared times CAB be equal to sigma AB. Now, when k goes to 0, we learn 2 things about it. First of all, we learn that sigma AB, which is a property of the boundary geometry, because it's the shear of U or of epsilon in the case of the Carrollian. This is a geometric feature. This should vanish. So this is a very specific geometric feature of the Carrollian geometry. It has to require this. This is the second one. But the first one that I quoted here, and this is the most important, is that by setting k to 0, this decouples the CAB, and the CAB becomes completely free. This is why the shear, this is the shear, and this is why we know that the shear is completely free in systems which are asymptotically flat, and this is, of course, a sign of the freedom to have radiation in these spaces. Right? This is at order R, and these are the conclusions that we reach at order R. Not very surprising, but naturally coming with the limit. The other order, which is order 1 now, remember this was the order no powers of R, R power 0. We had this function, which, as I said, was related to the Schouten tensor of the boundary, the Weil covariant fashion addition of the Schouten. Now, when k goes to 0, actually all this inside will have other powers of k, and it turns out that the output is finite. So what you find, I don't give the expression, but you will find an expression which is a tensor based on the various ingredients that you have on the boundary plus the shear plus the time derivative of the shear, which is what we call the news. Now, in this notation, using some covariant derivatives that we have introduced, what we call here the news, AB, right, it will appear in the next, is simply a time derivative, because this is the derivative along the vector, the time vector of the CAB, and it has a nice feature that This is metric compatible, so therefore this means that this is traceless and symmetric. And this is also traceless and symmetric. So it remains traceless through this derivative. Anyway, I quote that because it will appear in the next slides. I haven't used it here. Right, so this is what happens at order 1. Now, for the next orders, I need to introduce here some notation about the cotton tensor, because you remember everywhere in the expression of the metric and in the equations there was the cotton, the boundary cotton tensor. For those who do not remember, the boundary cotton tensor is basically a Weil covariant derivative of the Ricci, because the output is actually, or the Schouten, the result is, it's a Weil covariant derivative of the Schouten tensor. It's Weil covariant. Now, as much as we can expand the energy momentum tensor, introducing arbitrary functions, we can do it for the cotton, except that here is not an expansion. This is exact. The expressions that you have here are exact. The various pieces of the cotton tensor appear as a sort of polynomial, well, with negative powers as well, very specific, and the functions which are here are determined completely. So these are functions, well, these are tensors, Carrollian tensors, which are completely determined. These are not arbitrary functions. They are resulting from the geometry. This is as opposed to the energy momentum tensor, which is new. But I will, since those quantities will appear, well, of course, I don't expect you to remember all this, but they appear, and they play a role. So let's see what happens, therefore. So we are at order 1, and the next step is order 1 over R. This is where the anti-de Sitter energy momentum tensor was appearing. Now, and this was, remember, this was the expression of the anti-de Sitter piece of the line element. Now, we have to introduce epsilon, q, and tau as much as the cotton in powers of k squared, and demand that this is finite. So this will kill an infinite number of the negative powers that we had, because those were too divergent, but what will remain are the following expressions. In blue are 3 quantities which are at this stage free. They remain in the line element because they don't bring any harm for the finiteness. Some pieces previously more divergent are completely determined in terms of the cotton. So this is something that is new here, and I think it has still a deep meaning that it's not clear to us, is the following. Remember that what appears in this expression is delta Q. So this is a combination of the energy of the heat current of the energy momentum tensor and of the cotton. Now, the cotton has divergent pieces. The energy momentum tensor has potential divergent pieces. Those must cancel each other. And this is how, when going from anti-de Sitter to flat, those pieces of the energy momentum tensor are no longer free, but they are determined in terms of the boundary cotton tensor. So the boundary cotton tensor enters the dynamic. So this is why the Q, which refers to the energy momentum tensor, is now here determined by this ZA or Chi-A or these other letters. These are fully determined by the cotton. This is why I put them in red. This is not new information. But the new information here is that they determine part of the cotton tensor. And then, as I said, these blue are the things that remain. The others also remain, but they have powers, positive powers of k, so when k goes to 0, they're harmless. So eventually, this is the line, this is the 1 over R line element. 1 over R line element of the flat case with 3 arbitrary functions, epsilon 0, pi a, and EAB. All this coming from some powers of the energy momentum tensor. Now, these are free. Nevertheless, they must obey an equation, and the equation you find by considering the divergence of t equals 0. Take the limit appropriately. And for this, you find what we call the Carrollian equation. You find indeed an equation for epsilon 0 and pi a, which involve the Bondi shear and the news. You don't find an equation for EAB. EAB is present in the line element, but you don't find an equation for EAB by considering the limit divergence of t equals to 0. This is, again, this is not only technical, it tells that many of these functions, which are new, have a very different status with respect to the others, right? So just to show how what is the final sort of equation that you obtain, these are the two equations which arise from divergence of t equals to 0 when taking the limit k goes to 0. These are two equations for the two functions which were epsilon 0, remember, and pi a. What is here plays, or appears at least, as playing the role of a source. This contains the shear, this contains also the news, as well as pieces of the cotton tensor. So basically, all this part carries information about the gravitational radiation that balances the loss of energy and angular momentum. Actually, and I'm just flashing the result, this epsilon 0, which was the energy density of the energy momentum tensor, appears as being related to the mass, and pi a appears to be related to the angular momentum. The specific expression are given in this. So this is a dictionary between the standard quantities and the quantities that I have introduced here. Yes?
But this EAB, that is arbitrary at this stage, will become constrained at...
Will become constrained in the next slide. But it's very good. But this is good to insist because these are very different. So this is good to just let me repeat again what you said and what I said previously. You had only one equation, which was divergence of t equals to 0. This equation gives, there is a time component and a space component, and it gives the two equations, which are the famous Bondi flux balance equations, for epsilon 0, which is the mass, and for pi a, which is the angular momentum. This is what you obtain at order 1 over r. However, at order 1 over r, you still have in the line element EAB. This is not determined by these dynamics. This will be determined later on differently. Yes?
How are you choosing them?
Yeah, so you mean how do I know that the angular momentum aspect is this precise combination of a piece of the cotton, because this is what this is, and pi a? This is your question.
My question is, why are you taking that?
Ah, all right. This is what, this is, okay. There is, the simplest answer that I can give you is that you compare the equations, the Bondi equations, appropriately tuned for this gauge, and these equations that we find, and this is what you should do. The NA that appears in the standard Bondi equations written in the standard way turns out to be exactly this combination that I have presented here.
So does it transform covariantly when you do a BMS transformation? Maybe that's a way to check.
Well, they transform as they should. Exactly. So the pieces which are here, this is very good. Actually, this is at the heart of, but I will not discuss this myself. If you don't mind, I leave that to Simon, who will discuss these issues this afternoon.
Okay,
but the question is absolutely relevant. The transformation properties are exactly what they should be. Now, let me maybe answer, let me add one thing to the question of Simone. Just,
Yeah, so same as Simone. So if you contract this angular momentum aspect with the frame on the sphere, you get psi1?
Yes.
Okay.
Actually, this is very good because this, again, you laugh because I'll again say the word cotton, but this is exactly, there is a very good relationship between the cotton and the psis, part of the psis. Very good. So let me maybe add one thing. The second way of answering to your question is that the way that these combinations appear, the fact that, in our case, the momentum seems to be epsilon 0, whereas the momentum here is the mass, which is this combination, amounts to make a change in the fields, a transformation in the background fields. Now, because the background fields are not only the epsilon mu, and theta. The shear appears also to be a background field because this appears as a piece of the connection of the Carroll geometry, which is free, right? So, and you can change the choice of your background field determines the genuine expression between the various species of the momenta, because these are the momenta. Yes.
Yes. So just a question of notation. There are many different definitions of the angular momentum aspect that differ by quadratic terms in the shear, by gradients of the mass aspect times the retarded time. So there is a bit of a zoo. So which animal in the zoo is?
Okay. I will have hard time to give the genealogy of this animal very precisely. But, you know, I think this is the one in particular, if I remember, it's written in the paper because we have given the precise relationship with some of the other animals. I think this is the one that appears in Laurent's paper, right? And which gives the psi one. This is the one that we are using.
And so you will also recover the retarded time evolution for this n and m.
These are the equations, and these are those. So the two equations which are there.
So this is. Yeah,
this looks complicated because this is covariantized with respect to the geometry that we have. But these are the. I'm sorry if the nice equations of Bondi look so ugly here, but we can make them looking better. I think this is the work of Simon this afternoon. But these are the equations. So you have to trade epsilon 0 for m and pi a for n. And once you do that, and if you simplify the geometry, because remember here, the boundary geometry is general. So there is time dependence and coordinate dependence. Now, if you go to Bondi, you will simplify, and most of these things that appear on the right-hand side as the sources will be simpler.
Okay. Now, one last question.
Please.
These equations are constrained equations because they are constrained evolution over a null surface. Right?
Yes, yes.
The dynamics in flat space-time really is the matching condition between past and future infinity. So this is not here, right?
No.
Will you get it from any consideration?
The other equations, you mean?
No, the n at the and m matching in between the past of Scri plus and the future of Scri minus.
No, I don't. You want? Maybe you have a comment. I had a comment, but.
Yeah, the thing is that in the series of work which have been presented and which are going to be presented in this conference are only considering one piece of Scri, so which means past or future, because it's just a matter of changing the congruence for minus the congruence to go from one to another. Actually, when you are under the hypothesis that you are considering massless scattering, for instance, you can show that you can glue basically Scri plus and Scri minus along at space-like infinity, basically. And if you require that the gluing is smooth, basically it implies antipodal matching. So yes, we can have a Carrollian understanding of this antipodal matching at a geometric level, yes.
But it's not, I will not discuss it here.
No.
All right, so, no, it's fine. This is, well, I'm reaching the end slowly. So I'm here trying now to summarize somehow. This was the technical part, and this is what I tried to extract in answering the original question that was asked, right? So remember that we pose, we go to the boundary, there is a Carrollian structure. And remember, this Carrollian structure is captured in this set of fields. Now, if you have an effective action, you can consider the variation of the action with respect to these fields, and you will obtain what we would call the energy momentum tensor. Here, I have simply split the energy momentum tensor into the standard parts of the time, the mixed, and the stress, right? So this pi is the energy density, this is the energy flux, this is what we call the matter flux, borrowing the language from the Galilean setup, and pi a is the stress. All right, now, the two of these momenta are related, as we mentioned previously, to the mass aspect and the angular momentum aspect. So no surprise regarding that. Again, if you want to go really from one to the other, you have to just transform the background fields in order to make this passage very clear. The other two, however, are not free. The other two are constrained. They are not free. Those are free. Well, they obey an equation, which is the requirement that you have some invariance. Those are not free. They are just determined by the cotton tensor. The cotton tensor enters in this way, and I mentioned here in this remark that actually it enters in many other aspects, and in particular in the Newman-Penrose scalars that were discussed yesterday by Mark, possibly in memory effects. This was discussed by Glenn. We haven't done this in this way, but again, it will, in this case, if we can handle memory effects, I'm ready to bet that the cotton will enter there. Now, the other thing, and this is important, is that this is part of the geometry, but there is another part which is the Carrollian connection. This is, again, you have the connection on the boundary because the metric is Carrollian, the structure is Carrollian, there is a piece of the connection which is not determined by any constraint, so this is free, and this is actually the shear, and the conjugate momentum is the news. And when putting all these things together and writing the invariance, what you find is actually the flux balance equations, the one that I have presented here, they come under this principle. So this is not what I will present here. I will just mention the equations that I have obtained through the limit can also be obtained by doing a perfectly and exclusively boundary analysis. Let me mention before concluding just what happens at higher orders, because this is also an important part. You have an anti-de Sitter energy momentum tensor. There are higher Bondi aspects. Those are what we call, what we have called the Chthonians, because those are the ones that are deeply entering the bulk. At every order in 1/r, you need a new piece of information. Actually, the equations that those obey are obtained by requiring that the line element be finite. So if you go at order 1/r², you'll find a divergence. And the coefficients of this divergence will be the equation for the Bondi higher aspect coming at 1/r. So the EAB, for which we didn't have any equations, appear to obey an equation that is obtained when k goes to 0 as a requirement of finiteness. This is the equation that you find. And this actually, this is the equation that we find, and this, of course, repeats at every order. But this raises an important question here. The EAB appear to be momenta, but it is not clear what the corresponding fields would be on the boundary. So this is part of things that require still to be understood. And let me summarize and conclude quickly. So remember, the original question was, is there a boundary dynamics with fields and conjugate momenta that we can discuss as we had in the case of anti-de Sitter? And the message here is that the infinite component of the flat solution space, the infinite component, comes indeed from expanding the anti-de Sitter energy momentum tensor in Laurent expansion in powers of k squared. Now there are several sectors. There is the energy momentum sector, and there you have Carrollian momenta, which are dual to the structure, and some of those are locked by the cotton. And you have an infinite sector of higher Bondi aspects. Those are momenta, but in terms of purely Carrollian dynamics data, their dynamics is not known. We found the dynamics from the bulk in the limiting procedure, but how those equations could be obtained from a purely Carrollian approach is unknown. However, what is known is that there is a finite component sector, which is the Carrollian connection and the hypermomentum. And for those, of course, we master the boundary dynamics, because together with the momenta associated with the geometry, we find from the boundary perspective, the equations. This is not what I will discuss. This will be discussed. I mentioned that it has been discussed by Fiorucci last week. Jelle, I think, will also discuss this issue in an hour. Simon, so there is a certain activity around that. So now, beyond that, well, maybe I should also quote, finally, since holography has been discussed, if there is holography, because yes, I still want to say, I have 0, but can I finish this? Thank you. Yeah. Yeah, what I wanted to say is that there are several sectors. This comes back to the original discussion that we had. There are several sectors. One is the one of shear and news at order R. And this is what somehow has been captured till now with the celestial and Carrollian approaches in computing the amplitudes. But there is another sector, which is a sector at higher orders. And this is not known from the point of view of holography. Now, because it's an infinite set of data, you may actually consider that this is maybe not local. In that case, I would give another word to holography. I would call it allography because it's a different way of describing. And I think even in that case, there are actually handles in the k goes to 0 limit. And some works have been done, and then we'll heard about that by Roma this afternoon. I'm done. You can now say the 0. Thank you.
Okay, we don't have a lot of time left for questions, but there are a couple of urgent ones, maybe.
Well, Massimo said that there is a zoo of definition of angular momenta, but I would like to stress that this is a zoo not populated by animals, but by chimeras?
Yes.
Because most of these definitions are not good. In particular, if you require covariant transformations under BMS and that it is a canonical generator in the Noether sense, then there's a unique choice that sticks out. And some of the other choices, like this Psi1, have issues that can be shown explicitly. So I'm wondering if in your construction you could tailor the Carrollian description so that you actually get the Drey-Streubel covariant definition.
Well, we know things, but not everything is yet completely settled. We have this freedom, absolutely. But I think that at this stage, it's a little bit premature to answer.
Maybe I could comment that in this world of inverse of L3, there are the split expression of magnetic Carroll gravity together with matter. Therefore, maybe some connection could be.
Yes.
Some of the questions could be checked.
Thank you.
Other questions? No? Okay, so if not, let's thank Marius again.